squared, b squared, and c squared. And what I'm going to do is shear each of these squares towards the line over here. Now, what you're going to notice is that as I drag, oh, hold on, there we go. As I drag a squared towards the line, it stretches out. But what I want you to think about is that question on the side, are the areas changing as I shear the squares towards the line? Let me pull this one out a little more. There we go, we're on the line. We're on the line. You've noticed I've created a polygon. Now I'm going to take this one, c squared, and I'm going to fill it in to the edge of the right triangle here. Now, what you should notice of the areas, when I combine a squared and b squared, they make this sweet little looking polygon. And when I take c squared, it mirrors that same exact polygon. It'll have the same dimensions, same sizes. So that's just another proof of how a squared plus b squared equals c squared. Now let's work on some more problems. Let's take a look at a couple of examples involving the Pythagorean theorem and how we could use it in real-world situations. First, we're going to take a look at this example. In the diagram, a taut wire AB connects a point A on a vertical wall to a point B on the horizontal ground. A is 2 meters above the ground, and B is 0.6 centimeters or 0.6 meters from the wall. Find the length of the wire. All right, so first thing I'm going to do is take a look at the Pythagorean theorem, and I see that this section AB is my hypotenuse. It's a U, trust me. And then, so I'm going to set this up as length AB squared is going to equal AC squared plus BC squared. I'm just using these letters to note the distances. It's not so much that they're specific letters that I'm using, but just to talk about the specific distances. So that means AB squared is going to be 2 squared plus 0.6 squared. So AB squared equals 4.36, which means AB has to equal the square root of 4.36, and I'm going to go ahead and use my calculator for that one, and I'm going to get that AB equals about 2.09 meters. I'm probably going to need to write that in a different spot, so somewhere where you can see it over here. AB equals 2.09 meters. I rounded my answer correct to 3 significant figures. All right, let's take a look at this next one. In the diagram, AB and AC are 2 sides of a roof. AD is a vertical supporting beam, and BC is a horizontal beam. AB equals 3 meters, AC equals 2.1 meters, and AD equals 1.7 meters. Find the length of BC. Well, the first thing I'm going to do is find the length of BD. Then what I'm going to do is find the length of DC. Then I'm going to combine that answer to figure out the entire length of BC. So sometimes we need to make sure to take some steps, break things up in a little bit to see what needs to be done, make some sort of game plan, and then go ahead and work on the problem. So, using the Pythagorean theorem, AB squared, we're working on this first triangle, AB squared equals BD squared plus AD squared. So 3 squared equals BD squared plus 1.7 squared, which means BD squared equals 3 squared minus 1.7 squared. So that means I'm going to subtract 9 from 1.7 squared, and that's going to get me that BD squared equals 6.11 meters. So BD has to equal the square root of 6.11. Just meters. I'm just going to hold on to that for a while, and then I'm going to take a look at the next triangle, because now I'm going to look at triangle ADC. So now what I'm going to do, if we follow along this way, I'm going to say AC squared equals DC squared plus AD squared. So 2.1 squared equals DC squared plus 1.7 squared. So DC squared equals 2.1 squared minus 1.7 squared. So DC squared is going to equal 1.52, and DC is going to equal the square root of 1.52. Now I'm going to go ahead and combine my 6.11 and my 1.52 meters to get my final answer. So that's going to be the square root of 6.11 plus the square root of 1.52. With a little calculator magic, I'm going to round my answer to 3 significant figures, and that's going to get me 3.70 meters. So the length of BC is 3.7 meters. Now what I'm going to do is take a look at another example. The diagram shows the cross-section of a trough in which AB equals CD equals 9 centimeters, BC equals 12 centimeters, and the depth is 8 centimeters. Find the width AD of the top of the trough. So we're looking for this measurement right here. How are we going to do that? Well, first thing I'm going to do is break this up. We see that I have a trapezoid, and then I can make triangles here, triangles there. I know that if BC is 12, then this distance is also 12. Now I know that the depth of the trough is 8. I know that this is 8. Now what I need to do is find this value here, because I know it's a uniform trough, so I know that the distance from here to here, let's call this N, and let's call this M. I know that the distance from N to D is going to be the same as the distance from A to M. So let's go ahead and use the Pythagorean Theorem. I know that CD squared is going to equal CN squared plus ND squared. CD squared means I have 9 squared equals 8 squared plus ND squared. So ND squared equals 9 squared, which is 81, minus 64, which means ND squared equals 17. So ND equals the square root of 17. So it's the square root of 17 centimeters. So if I know ND equals square root of 17, then AM also has to equal the square root of 17. So what I can do to find the entire length from A to D is take the square root of 17 plus 12 plus the square root of 17 to get my final answer correct to 3 significant figures, again with some calculator magic, 20.2 centimeters. So the width of AD is 20.2 centimeters. All right, so these are some examples involving using the Pythagorean theorem. What we can also do is use the Pythagorean theorem to determine whether a triangle has a 90-degree angle. So this is known as the converse of the Pythagorean theorem. And what that pretty much means is that in a triangle, if the square of the longest side is equal to the sum of the squares of the other two sides, then the angle opposite the longest side is a right angle. It sounds really fancy, but really what it just means is that if c squared equals a squared plus b squared, then angle ACB equals 90 degrees, which means that then it is a right triangle. So what we're going to do is test that out. Here I have two triangles. Let's take a look at triangle ABC. So A is where are we? Okay, so side length BC is 48. Let's just call that side A. Side length AC is 55. Let's call that side length B. And then side length AB, which is 73, let's call that C, because it is the hypotenuse, so you should probably label it as the hypotenuse. Just to keep things simple, we want to remember that C squared is referring to our hypotenuse. All right. So C squared equals, C squared equals 73 squared. 73 squared equals 5,329. I did it all in my head, just right now. A squared plus b squared equals 48 squared plus 55 squared, which also equals 5,329. So c squared then does in fact equal a squared plus b squared. So that means that angle C is definitely a right angle because it's the converse of the Pythagorean theorem. It fits the Pythagorean theorem. Oh, hey, that should look more C-like and less O-like. There we go. All right. So let's take a look at the next one. Here we go. 30, 21, and 20. So what I'm going to do is label side P as 30, side Q as 20, and side R as 21. Same thing again, this time I'm going to check what P squared is. First, P squared equals 30 squared, which equals 900. And Q squared plus R squared equals 20 squared plus 21 squared, and you could already see what's going to happen because there's a 1. Anyway, when you combine those together, you get 841. Now that means, if you take a look, 900 does not equal 841. Whereas in the other example, 5,329 did equal 5,329. So because they are not equal, then we can say that p squared does not equal q squared plus r squared. So triangle PQR is not a right-angled triangle. That's it for now.